it really interests me is working with electromagnetic waves. When I did my PhD, I got excited about this and applied this to pavements. And always during my career, I have to keep going, doing things in this field. And giving here the diverse audience, I thought that I will be talking about a topic that it can be of interest to a wider group of audience. So again, I will be talking about transportation infrastructure assessment techniques using a ground-penetrating radar. This is a topic that it's dear to my heart. I've been working on it for more than 25 years. And I think we did have some really nice development in this field. So before I start, to make sure that we are all on the same page, you heard quite a bit about the word NDE, or non-destructive evaluation. So what does that mean? It means simply that we are trying to detect defects, do some measurements, and without destructing the specimen or the materials that we are dealing with. So there is no damage involved. A good example of this is when you go to a dentist and you have a decay in your tooth. The dentist, if look at your teeth, cannot find anything. But if they use X-ray, they will be able to detect that there is a decay, and after that, they will be able to resolve this without doing any damage to your teeth. So in civil engineering, we have been using this quite a bit. A simple way, and I'm sure many of you have been seeing this, is you get a chain and you drag this chain on a bridge deck and you listen. If you find that there is a different echo, this means here that you may have a void or you have a delamination. Actually, this is a scientific way, which depends on the acoustic emission. We can go this further and use a mechanical waves, such as ultrasonic or impact echo. The waves that you are sending now, it depends on the physical properties of the material, which means here the modulus of the material, the Poisson ratio, and the density. And the speed of the wave and the kind of type of waves that is developed, it tells us something about these materials, and we'll try to detect some problems. Here's impact echo, where you are using simply a steel ball. When you hit it on a structure, you have a receiver. This receiver takes these waves that it generated, which is a mechanical wave. By analyzing these waves, we'll be able to understand here the properties or any defects in the material itself. We can use ultrasonic, the same when you go to a doctor, when they use this to see if there is any problem in your kidney. We're using this also for the structure. And based on the velocity of these waves inside the material, we can detect something about the material itself. I'll be talking today about electromagnetic waves. Electromagnetic waves is a big spectrum here. It can go from hundreds of meters, the wavelength, to less than nanometers. And during that time, you see some terminologies that we are using all the time, such as the radio frequency, which is in the 100 meters, the microwaves, such as the one that you are using at home, which is in the centimeters level, and that's the one that I will be talking about. Infrared, which Joe has done an excellent work on infrared in order to detect segregation and detect also the variations in the temperature of the materials, which tells us if you're going to have a problem in these materials in the future. So the infrared usually is in the millimeter wave length. X-ray, which going to get smaller in the micrometers, and so we can see here fibers orientation in the concrete, which supposedly to reduce the cracks or kind of dissipate the energy of the cracks in the concrete. So all these are non-destructive testing. But the one that I'm going to be talking about today is ground-penetrating radar. So what's ground-penetrating radar? It's the same radar that you are using for detecting airplanes. You send electromagnetic waves. These electromagnetic waves go. It hit an airplane, which is a metal. It comes back. The speed is the speed of the light. So if you take now the time, if you calculate the time that it takes for this to go and come back, and you know the speed of the light, we will know exactly where that airplane is. Simple enough? Okay, we're going to take this technology now and apply it to civil infrastructure. So we can now, instead of send it in the air, we're going to send it into the ground or civil engineering materials. By doing this, we can estimate if you have any earth sediments. We can look into any buried materials. We can use it for detecting mines. And also in civil engineering, we can use it to evaluate condition of civil infrastructures. Like in Vietnam War, they were using this same basic idea to detect any tunnels that they have with the enemy. So For our application, instead now, this material is going through the free space at the speed of the light. It's go through a material. If it's go through a material, it's going to be at a slower speed. The slower speed is coming from the speed of the light divided by the square root of the dielectric constant of the material. Each material, it has a dielectric constant. For example, if I have a dry sand, this wave is going to go much faster than if I have a wet sand. And if I have a saturated sand, then this material is going to get much slower. So what is the dielectric constant? Actually, it's a complex number where you have a storage for the energy, and you have the dissipation of the energy. Using this technique every day at home when you are using the microwave. How many of you has used the microwave to heat a sandwich wrapped with a foil? Okay, people start laughing. So what does that mean here? You know that something wrong happened, right? It starts sparkling. Why did it do that? Simply because it's a complete reflector. So the electromagnetic waves go there. You have a metal. It reflects it. Okay? If you have your food has a little water, because water is very lossy, it will just heat this food. If you have your food completely dry, it's going to take much, much longer. But if you have your food frozen, it's going to take a long time too. And the reason, but it's water. And water has this lossy thing. It will make it heat. But because it's structured, it's like ice. So when it's structured now, actually, the dielectric constant is going to be exactly or similar or a little above that of the air. So actually, I think in the early 50s in Greenland, there is an airplane that it hit a mountain of ice because they could not see it, because the dielectric constant is the same as almost the air. So that being said here, if we know what's the dielectric constant for the materials that we are dealing with, now we can use this to our advantage and learn something using ground-penetrating radar. So the air is the reference, which is 1. Water is very lossy, 81. Asphalt concrete depends on the aggregate you are using, from 3 to 10. Asphalt binder is around 3. Excuse me. Limestone is usually around 6, 7, maybe 8. Granite is less. It's usually around 4. It can be 5. And then you go to the dry sand and so on. Clay, it depends. It's very big range. Because if that absorbs the water and the water is connected to the clay, then it becomes structures. It becomes low. If the water is free, then it becomes high. So this is very important to see what kind of materials we are dealing with. So now we're going to be using this here as part of what we refer to as scattering. So I can use this for structures to see if there is any segregation, delamination, reinforcement. For pavements, to see different layers and distresses. And railroad can use it to find what's the large air void and if you have any fouling, which is clay in the voids of this. So as I told you, that's when I was young and looking good. So I did work in this field in electromagnetic waves at that time. And interestingly enough, that at that time I was working on the stepped frequency signal, which now people are getting back to it. But there is different approaches, frequency modulated and synthetic pulses GPR, which I'm going to mention a little bit because it's just start coming again. And the GPR is the one that it's mostly used, which I will spend most of my time. So what does that mean here? It's usually around 1 nanosecond. The principle is you send the signal and you receive it. From the received signal, you can learn a lot about the materials. And I'm going to go here and explain that. But before I do that, I wanted to differentiate between the different antennas that we can use. Excuse me. First, we have a ground couple antenna, as you can see here on the top picture. And this usually in contact with the surface. And you cannot do it at a speed more than 10 miles an hour. So we are restricting here the survey speed. The second one is that you have it as air coupled. And usually it's around 1.5 feet above or so above the surface. And if you put it on the van here in the back or in the front of a van, you can now do the survey at a highway speed, like 60 miles an hour without any problem. And these antennas can be monostatic, which means the transmitter and receiver are in the same antenna. Actually, they are not in the same exactly. There is a distance, but they put them in one box. The bistatic, where you are using 2 antennas, like one on the left and one on the right. And of course, recently we have the 3D GPR, which is an array of antenna, and that's used the step frequency, like the one that I worked on. Gosh, that was more than 25 years ago. So that's a new thing that is going on right now. So to make sure that we follow what I'm going to be discussing, I'm going to go through the concept or the principle of how the GPR works. You have on the car a GPS, or distance measuring instrument, DMI. That one sends the signal to a signal generation, okay? The signal generation, which is this one, will generate a signal. The signal, it goes to an antenna, which modulates this signal and send it to the ground. When it goes to the ground, the air has a dielectric constant of 1. When it hits the ground, if the dielectric constant of the ground, let's say 5, some will go through and some will be reflected. So now I'm seeing the reflection from the surface. It will go through the material, the first layer. When it gets to another material, it will have different dielectric constant. You have another reflection. And during that time, you lose some power. So it just keeps going. Whenever there is a different dielectric constant, it will reflect it back, okay? But at the same time, you are losing some power. So at a specific depth, you start now losing complete power and you are not getting anything back, okay? So usually, if we want to see something deep, we wanted to use a big wave. If we're using a big wave, then my resolution is going to be smaller. So there is a trade-off here. If I'm using this for measuring an overlay, I will make sure that I'm having a very small wave. So we can use this now direct or indirect applications, such as for the evaluation of structures. Moisture, I said it's very lossy. I can detect that very easily. Reinforcement is a complete reflector. I can see that very easily too. But I want to use it now for some applications like layer thickness estimation, quality control, quality assurance. I want to use it for measuring density of asphalt. And I'm going to come to this. This is important. If we have time, I keep some slides at the end to talk about also some work that we have doing for the railroad evaluation. So for concrete pavement, where you have reinforcement, I get this vans, and it moves. And as you can see here, you have all these parabolic shapes that it's happening because of the rebar. They are complete reflectors. Now, these parabolic shapes is not because the rebars are circular, no, but because the pavement, the truck or the van is moving, and it's far away from the rebar. So it shows here this distance. As it's getting closer, the distance or the time will be much less, so it will end up appearing as a parabolic. Okay? So it's very easy to see that. And you can accurately now measure the cover depth that you have on top of the concrete, which is really important. Some of the rehabilitation techniques that we are using for asphalt concrete overlay is something called steel reinforcement mesh, or a mesh track that we are using in order to reinforce the materials to prevent or retard cracks from joints and underneath materials. So this technique here was used to detect where you have a problem during the installation that resulted in problem on the surface. So it clearly can be seen without even analyzing the data. Dan Ryan Bridge is one of the busiest bridges in Chicago. It's more than 4 miles, and it has 6 lanes in some areas, and you cannot close this. And one of the things that they wanted to do is to rehabilitate this bridge. To rehabilitate this bridge, they must know what's the cover depth, and these things can vary. So if you want to go and take some course, it's going to be tedious. You're going to close this. So what we did, we used the GPR at 45 miles an hour, and we use it at 5 o'clock in the morning when, I guess, no traffic, and we did not close the traffic. We just have some vehicles behind us just to provide some protection, and we were able to get the cover depth, and that saves millions of dollars because that dictates what approach of rehabilitation they have to do. Many of the bridges that you have across the country, historic bridges, we don't have any information about them, and we don't have any idea if they're going to survive the loads or not. So GPR can be used on the top, where you can start using this to find the cover depth and reinforcement, and then you can go at the bottom and try to know where is the bottom reinforcement, and from that get some information about the structure of these bridges. Interesting projects in a major intersection in Chicago area, where we have an abutment built, and after they built it, they put the girder, and the girder filled, and some people get killed. Now, the question here, is this safe? If they don't know, this means that they're going to have to take the whole pile abutment out, and that's very, very costly. It's not just the money, it's the time. So they came to us and said, can we know if this is, you can see here the reinforcement on the top, how it's affected, right? So this is, we don't know structurally what's happening in the abutment itself. So GPR can be used, and it can show where the delamination, where the problems are, and how the reinforcement inside still aligned or not. And based on that, they found that they can fix these pieces there and continue, and they did, and now it's in use. So something like this becomes very important for the use of GPR. As I said, I'm a pavement guy, so I can now switch to pavements. So how it works in pavements, you send this electromagnetic waves, it hits the surface, you get an amplitude. It goes through the material, have a different dielectric constant, you have another reflections, and so on. So the picture that you are seeing there, it's real data, it's not a drawing, so this is what you get. If you take this signal and you take these measurements every 1 inch, 2 inch, whatever you want, and you put them and stack them next to each other, okay? Just put all these signals together. As you are driving, you're going to see something like this. So here's data that it has not been analyzed, completely raw data. That's how you see when you are looking at your signals. All what you're doing is just you stack them next to each other. Now, if I know what's the dielectric constant for this layer, this is here the time that I'm measuring, I will be able to tell you what's the thickness. Does that make sense? Okay. So this is the whole idea behind this. Now, the way that people are using this in the field is they take a copper plate, they put it on the surface, and they take a signal. This signal represents the signal that you are sending, because we said it's a complete reflector, right? So then they take the copper plate, take a measurements from the surface, and they say that the dielectric constant for the whole layer is the same. And they use this simple equation. So now what they are dealing with is the amplitude from a cover plate, or what you are sending, and the amplitude that you're getting from the surface. From that, you get the dielectric constant for this asphalt concrete. Now, this is okay if I'm using a material that is homogeneous, or if I'm using a material that is new, I just paved. But with time, this material is going to age on the surface, so the dielectric constant is going to be different, so this technique will not work. So this is usually what everybody's using in the field, a dielectric constant like this. So simply put here, as the dielectric constant increases, the surface reflection amplitude increases. So if you get this material aged, the dielectric constant is going to be different, so the dielectric constant will not be constant throughout the material. So we have to find a way that will allow us to measure the dielectric constant for the whole material. So what I did, I said, if we can get what's the signal that it's reflected underneath the asphalt layer, we'll have a better idea. So put copper plate here, as you can see, under different layers, and I can see the reflections. By the way, what I'm presenting here is completely raw data. And if I start looking now into the signal I'm using here, as it goes through that layer, some will be lost when it reaches the bottom. Some will be, it will be completely reflected. Some will be lost through the material again. When it goes to this surface, some will be going to the surface, some will reflect back, and just keep going. I think if we get the first two, that's more than enough. Actually, the first one will be enough to get us an idea about the surface. If I get this one and this one, that should give me an idea, a very good idea about the whole layer of asphalt concrete. So in order to take this and use it in the field, because I cannot put a copper plate in pavements, I mean, it's going to be impossible whenever I build a pavement, put a copper plate. So we came up with a technique which called the CMP, or common midpoint. So this simply is, I get two antennas, transmitter and receiver here, and put a transmitter here and receiver here, and I can now measure T1, and I can measure T2. From the T1 and T2, I'm using here just simple triangle analysis, and can find now the dielectric constant based on this T1 and T2. And of course, I know the distance between the two. Now, the dielectric constant that I calculate here is the dielectric constant for the whole layer. Now, the problem is that such a system does not exist off the shelf. But this system exists, where I can put an antenna on this side, an antenna on this side, and a transmitter and receiver in the middle. I'm using also Snell's law, which tells me that the sine of the angle here, the incident, multiplied by the dielectric constant of the air, which is 1, is equal to the dielectric constant of this layer multiplied by the sine of the reflected signal. Okay, so I can do now this. If you look here into x note, it's simply equal to x1 plus 2, this distance from here to here. So again, I'm going through very simple analysis here using triangles. The exceptions here is theta t, which is this one. I can calculate it based on the T1 and T2. But if I want theta I here, I have to use MATLAB or an iteration approach in order to get it. If I get that, I will be able to calculate the dielectric constant. And now I know what's the dielectric constant using these two techniques. Now, are these antennas available in real life off the shelf? The answer is yes. The only difference here is I have to drive my vehicle at 10 miles an hour because this one is in contact. So we came up with a new technique here, which called the extended CMP. And this one here, now I'm having the transmitter and receiver all up in the air, and you can drive at 60 miles an hour. And this is how it looks now. And this is how you put it on the back of the truck. This is the truck, and this is the two antennas, and you can use this as a transmitter, and this is as a receiver. Actually, we use this one with this one, and we use this one here with this one. So it depends how this is the schematic. So this is part of the iterations that we were using. Now this has now become a little complicated here, so I don't want to bother you with all these equations, but this is here how we can solve these problems. You have 4 equations, and you have 4 unknowns, and you will be able now to calculate. There's one trick into this here, is if I'll go back here, if these two antennas, I can make them far away, I will be able to have my measurements more accurately. If they are close, then the difference, we're talking about nanoseconds here. So we're talking about very, very small time. So small error can make some good difference here. So the further you have them, the better it is. So that's the only concern that we have, but we use this very, very successfully. So we have these 3 methods, but either one you are using, we have to automate this for measurement of the thickness. So the first thing you do is you take the data, you pre-process it, and you try to detect any kind of difference between the layers. Before I go further, I wanted to emphasize one important point here, that GPR is not an X-ray, okay? So everything depends on the dielectric constant. Let's assume that you have a concrete pavement, and underneath it a cement-treated base layer. These are completely different in strength, in modulus, completely 2 different materials, right? If the dielectric constant, which is good possibility it might be, if the dielectric constant is the same, the GPR will see them as 1 layer. Is that clear? So the difference here, it has nothing to do with the strength. It has only to do with the dielectric constant. That's an important concept about using electromagnetic waves in comparison to use mechanical waves. So we do detect the interface between the layers and then see if there is any distress. So we separate it, we calculate the dielectric properties, and then we present the thickness. So this is here how the data use. We do the calibration first. When you get your 2 antennas here, they're definitely going to talk to each other. So we need to eliminate this. So what you can do, you take the 2 antennas and let them face the air. If you let them face the air, they're still going to talk to each other. So that will allow us to eliminate this, what we refer to as the coupling, which is the first part here. Then I know this is coming from the air until you reach the material, so that's where we're going to start. And then you start having reflections or pulses based on the pavement that you have there. So this is here a raw GPR data, and we start now using some analysis to detect the threshold that we wanted to consider as a layer. Like whenever the amplitude reaches this value here, consider this here that this is a defect, this is a layer, or whatever, and we start our analysis. By doing this, we'll start now having the different layers based on the time domain, as you can see on the left. The time domain now, we can use it to calculate the dielectric constant. This is here the dielectric constant, and you can see they vary quite a bit. They have some difference because it's completely inhomogeneous material, and from that you will be able to calculate the layer thickness result. So we have a program that will allow us to do this. If we use this at the beginning, we used it for 18 pavements that we don't know anything. They were old, new concrete, asphalt, and it just gave some really good results here for these 18 pavements that they varied from like few years to 25 years and so on. But if we use it in a new pavement, as you build layers, you can see here that the error is getting less and less as you are increasing the thickness, which tells us here that there is a little systematic errors, which is like if you are talking about thickness of 2 and 3%, that's almost the error that you are getting from a core. So the measurements for new pavements, it's really good. Another thing here is the GPR resolution. Like this here, a pavement section where you have different layers. If you look at the signal here, I can see this, but I don't know what's happening here. So one way to go this is to go ahead and create this again. So I create this signal again, okay, synthesize it, and this is the one measurements using least square until they are on top of each other. When they are on top of each other, I can now separate them for layers and see how can I get these kind of shapes here. So in this case here, you can see that this on top of this will give you something like this. And that's where we start now by using this kind of iterations approach, separate between different layers, and get into the different layers that we have for these pavements that correspond to this. Another thing that we recently have been working on is that we noticed here that this layer, if you have this very thin, the thinner this layer, as you can see, the less I can distinguish. The more now I'm increasing the layer, you can see how the signals start distorted until you reach a point where you can see this very clearly, right? So at one thickness, you can see everything clearly, but the problem if you have it very thin, that's where it needs some analysis and signal analysis in order to guess this or to find this. So we are using the regularized devolution approach, and that allow us to measure this even at less than 3/4 of an inch thickness, which is really considered very accurate for doing overlays in asphalt concrete. Switch a little bit here into the 3D GPR, as I mentioned. This is a frequency step, but over a big range of frequency from 200 megahertz to 3 gigahertz. And this is here the system as we build it just for the lab testing. This is here the system that we have, and we put it on wheels, and we're taking the measurements. Now, the beauty about this that it will take the measurements over a wide range. So if you have a bridge deck and you want to cover the whole bridge deck, this will be an excellent way to do it. The only problem right now is that we cannot get the resolution that we can get as I showed you before. I mean, the resolution that I mentioned for the thickness, I said we can measure a thickness of 3/4 of an inch and even less, but the accuracy of that now, we are being able to get the accuracy really, really nicely, and I'm going to show this in a little bit even when we talk about the density. So the accuracy for this is becoming really good. This one, it's not as good yet. We're working on this. So what we did, we have some sections where we have plates, and as you can see, the vertical slicing, it shows the plate here, but this is the beauty about this, that you can also have the horizontal slicing. So you can build this in 3D and see where the locations of the different layers, if they vary, or if you have defects, what the size of the defects, and so on. The only catch we have with this now is the resolution still not as good because we have a big range of frequency, and we're still working on this. This is some of the stuff that we have been working on, which is the Shannon-Whittaker interpolation that will really allow us now to improve the accuracy of the measurements of the thickness or the detection. So this is ongoing work in this field, and I think that we will be getting to very good results hopefully soon. But the beauty about this is that you have 11 receiver and you have 11 receiver and 11 transmitters that they are connecting with each other over a big range of frequency. The reason why we don't have this kind of big resolution is because of the variations in the frequency that we have, okay? Because when you are getting to 200 megahertz, the lowest, then your wave is very big, and then your resolution is going to be less. Again, I'm going to say here that the higher the frequency, this means that you have lower wave. This means that your resolution is big, but your penetration is less too, okay? So if I have a void in a highway, which it happens, at 20 feet, can I use a typical GPR? No, I'm going to be using one in the megahertz. Can I see the voids? Of course, but if it's 1 inch, I will not see it at 20 feet. If it's at 20 feet, I can see maybe half a foot or something, so it has to be big, all right? So let me move into an area that it's important, and a work like this is really needed, which is the density of the asphalt. For the people who have not dealt with asphalt concrete, it's a very complex material. I mean, it looks like simple things we put in the pavements, but if you look here at the picture, it's just an aggregate and asphalt. If you get closer, you can find the structure here between the air and the asphalt and the void. And even if you look into the asphalt itself, it's not asphalt, it's a mastic. It has in it small dust fibers, whatever we are putting there, and that makes it a very complex materials to deal with. But there is one thing that's important for us is when we build these pavements, we need to know what's the density of this pavement. It is critical. That's how contractors are paid. They have to meet a specific density. And if we have too much air void, it's going to age the material and cause raveling and problems. If it's too little, you're going to have bleeding, which is hazardous, skid resistance problems. And you may have rutting or shoving in the material. So it's critical that we get the right density. And it's part of the quality control, quality assurance. So during the construction, it is important to get the proper density. And we're trying to avoid under or over compactions. And that's not an easy job for people who work in the field. It really requires some good experience. So measuring density techniques, currently we have cores that you go to the field, take cores, but how many cores are you going to take? I mean, you're going to change it to a Swiss cheese if you're going to take many cores. So we need to be, I guess, reasonable about this. And there's another important thing, that you do this after the fact, which means that it's already compacted. So if something is wrong, the only thing you can do is just to take some money from the contractor, okay? Second is using nuclear gauge. Nuclear gauge is a radioactive, you need to register, but still it's a spot test, okay? And I'm not sure about the accuracy. I mean, it's the best that we have, let's put it this way, and I will stop it right there. The non-nuclear, it's similar. It's using the electromagnetic waves at the very low frequency, and also it requires surface contact. Recently, they introduced, the intelligent compaction. This stiffness change with temperature, because the asphalt concrete, as the temperature is lower, it becomes stiffer. It also has to do with what kind of support you have underneath it. It is an excellent technique when we are using it for subgrade and base and unbound material. When we start using it for asphalt concrete, then we have to create some kind of a database that consider the temperature as well as the support from underneath it. So the people who are working on this for asphalt concrete, they know that they have to create some database, maybe using neural network in order to have a better results for this. So how is the electromagnetic waves can work for measuring density? As I said before, electromagnetic waves has nothing to do with the physical properties. It doesn't tell us anything about the modulus of the material, but it tells us about the material from a dielectric constant point of view. So if I look into the asphalt concrete and I know what's the dielectric constant of the asphalt concrete, there's something called the mixture or the volumetric mixture theory. This theory here, it relates the portion of the volume with the dielectric constant for each components to the whole material or the composition of this. So simply, if I have the dielectric constant of asphalt concrete and its volume, now the dielectric constant for each component, if it's like aggregate, asphalt, air void, and the portion of the volume of these three materials, from this I can know what's the dielectric constant of the asphalt concrete. So keep this in mind here. That will take us now to simply that function of the dielectric and volumetric properties of the component of the asphalt concrete will allow us now to know what is the dielectric constant of the asphalt concrete or the density. Okay, so let's see how we're going to do this. This is the GMP. It's the specific gravity of the asphalt concrete, or indirectly you may call it the density indirectly. So this is here the equations that we developed. It's a model that we developed. As you can see, this model here, it's based on the dielectric constant of the components as well as the asphalt concrete and the portion of the volume of each one of these components. So if I look at this model here, I can calculate the dielectric constant of asphalt concrete from what I presented earlier. The dielectric constant of the binder is 3. I know that. The maximum specific gravity for asphalt concrete, we definitely know it when we go to the field. The binder content, we know it in the field. That's something that we should do. The only thing that we don't know here is the dielectric constant of the aggregate. The effective specific gravity of the aggregate also, we know it. But the dielectric constant of the aggregate, we don't know. But if we can measure this as an area like Seattle, where we know what kind of aggregate used in which location, and put this in the equation, then I'll be able to get the density. So let's see what we did here. We put a big site, and this side you can see the copper plate here on the side of this, and we start paving this as a big section. So we put copper plates so we can know what's the complete reflection through the asphalt layer, as you can see here in these sections. What's on these sections? Of course, you cannot maybe read it. It's so small, but you cannot trust what I'm going to say here, that you have different air void, different density on each one of these layers for all these different mixes. So we have different mixes from here to here, and each one, it has an air void like this is 4, this is 6, this is 9, and this is 12. And this one here, we varied also the thicknesses too. So we start taking the measurements, and we have copper plates there. This is how the sections look like when we were done. And we start now the procedure of prediction of the density. First, we collect the GPR data. Then we obtain the asphalt content profile using the methods that I explained earlier. And then we put the equation. In this equation here, we know all these variables. The only thing that we don't know is the dielectric constant of the stone. So it's 1 out of 2. It's either I go and take a core and back calculate it, knowing everything, and calculate the dielectric constant for the stone and put it here and continue. So you need a core or 2 from the whole sections. Or I can create a library. Either way should be fine. Then I can calculate from that the density using the models that we developed, and we can calculate the air void. So this is here an example that we used. This is here the GPR survey. We find where the copper plates, we take this data, we analyze it, we find what's the dielectric constant for all the different sections. Of course, these are transition zone because you cannot kind of stop and have a different thicknesses. So you have to have a transition during the paving process, okay? So it's more of a construction related. So you get the dielectric constant. In this case here, we found that the dielectric constant for the stone is 6.1. We put this in the model, and we get now the bulk specific gravity, which tells me what's the density that I have for each section. We took some cores, and we looked, and this is here the density that you have across the section. Please notice here, the dielectric constant. Please notice here that the dielectric constant is going to be changing as you are moving. They are not constant. It's inhomogeneous material. But we took core, and also we did the measurements, and you can see that they are all fitting on the line that we have. How accurate the data we have? When we measure it in the cores, that's what we got. When we predicted this, and this is the relative errors that we have. So we have really good accuracy. But of course, we have some good control conditions. So let's take it to the field. So we went to Illinois 72 in Chicago. And this is the sections that have been used by traffic. And we have really different materials, quartzite mix, very fine mix, SMA, and sprinkle mix. Sprinkle mix, maybe I should mention something about it here. In Illinois, we don't have good aggregates. It's all limestone, and of course, it's not very good aggregate to have it on the surface. And usually, it costs like $18, $15 per ton of aggregate. But if we want to have really good aggregate, we have to import it from Wisconsin at $45. So that makes it very expensive. So the sprinkle mix is simply to use the limestone and then get some of these quartzite and coat it with asphalt and just spread it on the surface during the compaction. And that will give you very good friction, safety, and at the same time, I guess we had really very good success. Let's put it like this. So we included this in what we are looking at. So the relationship between compaction effort and GRP data, temperature has no effect We know that theoretically that should not have any effect, but we looked into it just to make sure. And then we verified the model that we have. So if you looked here, the quartzite, this is the GPR, this is the nuclear, this is the GPR. So you can see here they were similar. This one, it was very, very clear here that the GPR was way, way much better, and the same for the sprinkle mix. So when things were a little different from the calibrations that you do for the nuclear gauge, then it will just go. Okay? So the nuclear gauge depends on the calibrations that you do. Of course, 3% is still very good. I'm not saying that it's bad, but I'm saying here that this is a better approach. So during the compaction is the key here. I don't want to do it after. I want it to have a technique that will allow me to measure the density while I'm compacting so I can do the changes. So what we did, we looked into this and monitored this during the passes of the compactor. So the more passes, the higher density until you reach a point, and then it becomes flat, and sometimes it might drop. More surface moisture, this is a real problem for us, which means more reflection. So we need to see how we're going to address this, because that will mask our results. So the preliminary test, we have the GPR on the side, and we have the compactor moving back and forth, and we have this automated GPR just go after each pass, take a measurements, and go back. Okay? And we were able to get here it's called we call it the normalized feature value, which is related to the density. And this is the number of passes. So you can see that this is now increasing, and then it will start to flat. So for the people who look at this, they can tell you when to stop. That's really important. So you don't have to spend more time compacting and getting no results. So this is a big, big achievement by itself. Second, what we are trying to do is to put this in a compactor, connected, of course, with a GPS, and let the person who drives look at this and see when to stop. But we have a challenge. For the people who have been in the field, they know when they are using compactor here, they have a spray of water. And if you have a spray of water, that's going to really mask our data. And that's a challenge, okay? So if you look here, we looked at some data. This is when it's dry, when it's wet, okay? And if we normalize it, you can see here that the one that it is blue is the one that it is wet, while the real one is the red one, which means here you have a shift. We need to correct for this shift. So the effect of density variation GPR signals, we use finite difference time domain results. And I want you to look at the simulation that we did. We have the simulation here for different dielectric constant. This is the simulation. And I took the top one, and I draw it again, okay? And I looked at the real one here, which is similar to the simulation. So I was able to simulate that really nicely. What I would like you to do now, when I was putting the water here, you look at the curve, and something will attract your attention. That when I change the dielectric constant before, the whole thing is moving, okay? Because of the dielectric constant. But when I put the water in, you can see in the upper range of the frequency, things are moving, but at the lower range of frequency, it's not. And now we're going to be using this for our advantage, okay? So if I get closer up here, you can see this big difference here. This is the dry, okay? This is the wet. And as I let it dry, it starts coming down, but it's all in this area. So this area, there is nothing. But this changed with the dielectric constant, but not with the water. So I guess you got what we wanted to do. So what we wanted to do now is to focus on this area. So if you look now at the cutoffs that we have for the frequency, the original data is the blue one. If I filter the data between 0.2 and 2 gigahertz, you get the purple. The red one is between 0.2 and 1.5. And the one here filtered between 0.2 and 0.8 gigahertz, it's not affected. So now what we wanted to do is to cut it. The error was 6.2. Now, when water evaporated, of course, we wanted to get the dry value. And using this bandpass filter, we were able to get it back without any problem. So what we did, we just filtered the data used between 0.2 and 0.8, And this is affected just by the change in the density and dielectric constant and is not affected by the moisture. Okay? So we are getting advantage of this. So the feature value stays at 100%, and that was within 1% regardless of the water amount that we were using. So I think, am I on time? Okay. So in summary, GPR provides quick and reliable information about the subsurface characteristics when appropriately used, and I'm going to emphasize that point. Pavement layer thickness is not a big deal now. We can measure this with accuracy if we know what kind of antenna, what kind of frequency we wanted to use for that application. The density predictions, we have really good models now, and we are using the mixture theory. And recently, as I said, we were able to isolate the impact of the moisture, which was a headache, I would say. And it may be used successfully now for compaction monitoring, even if you don't want to isolate the moisture, because it can show you relatively when you achieve the compactions in spite of the existing of the water. So the effect of moisture on AC density predictions during compaction now can be isolated. And with that, I think I'll be more than happy to take any questions. I do have something about the rail, but I think with time it's good to stop here because some have classes. And I will entertain any questions that you may have. So thank you so much. You can start.
So I think the measurement is really the reflective signal, right?
Yes, reflective signal,
I
of course.
If there's like a pothole pavement surface, is that being measured at the surface thinner, much thinner, or actually you see the dig of the surface now?
Excellent, excellent question. He said, let's assume that you have a depression on the surface. I'm repeating the question. Let's assume that you have a depression on the surface. Does that mean that the GPR going to detect this depression? In GPR, what you're going to see is the pulse that it's interact with the surface, okay? And from the time that you send it. So this one here, it will show you that there is an increase between the time that you are sending the signal and hit the surface. So you can see an increase now in that distance. Let's say that you decide to go with 1.5 foot, now it's 1.6, you will be able to see that. Now, for the asphalt concrete, at the minute that it hits the asphalt concrete, now that's when you start. So if the thickness remaining is an inch, you will be able to see that 1 inch. So does that answer your question? Yes. So it's always calibrated to the surface. So if you don't want to see that pothole at all, what you can do is to calibrate to the surface, and anything above the surface, you can just take it out. So in that case, it will appear to you as you have a spot where you have a much thinner pavement. Yep. Questions?
Go ahead.
Okay.
So this is really interesting because I haven't studied pavements before, but I'm curious with this technique, are there imperfections that you can't observe that maybe traditional methods would observe even though they're really, really expensive?
If I understand you correctly, you said, can I observe something that usually is not normal?
Well,
is that what you were saying?
What I'm asking is, are there aspects of the pavement structure that you can't observe
In this one?
in this way?
Yeah, the answer is yes. The question is there something that sometimes you cannot see with this technique? And the answer is yes. As I told you, this is not an X-ray. And I gave maybe an example. If I have two materials that they are completely same dielectric constant, I will not be able to see them. However, which I did not present here, sometimes we deal with asphalt concrete that they have different layers, okay? So the one on the top, it has a different aggregate size than the one underneath it, which is maybe 1.5 inches, and then you have maybe 2 or 3 inches, that they have different aggregate size, and accordingly, they will have a different asphalt content, but they have the same air void. Now, the dielectric constants between these two, it could be maybe 0.5. Now, that one where we require very detailed signal analysis, and then we'll be able to detect it. I have not seen a material, I gave this as an example of saying like asphalt, like concrete and cement treated, if they have exactly the same dielectric constant, I have not seen it with detailed analysis that they are exactly the same. But if you want to do it like rough measurements, you will unfortunately see them the same, so you will not be able to distinguish. But remember, we're doing research here, so we're getting into the details of the signals in a little deeper. Mm-hmm. But some of the things interesting that I've been seeing, like in pipes, you can see them. In one case, we saw something really strange, and we digged in, and we found that somebody's sneakers was in the pavement. So you can see some weird things, actually. So I'll take Don.
So when you're dealing with these mixtures, like
yes.
in a concrete, why do you not see it as a whole bunch of reflections if you're going through a layer of concrete, going from the
excellent question
to the aggregate and back
yes.
and forth? Why are you not getting a bunch of reflections?
Excellent questions. Imagine here that you are in a boat and you have a wave coming towards you, okay? You are in a small boat and there is another guy in a big boat. The wave that is coming going to affect you much, much more than it's going to affect the big boat. The big boat will not even feel it. Does that make sense? Okay. Excellent. So the air voids that we have in asphalt concrete, they are very small. Let's assume they are 1 millimeter. I mean, they are smaller, but let's assume it's 1 or 2, whatever. The wave that we're sending there, this wave is maybe, within the asphalt concrete, is maybe 3-4 centimeters. In air, it's maybe 8 centimeters, okay? It depends. So they are not seeing these kind of voids, and it's assumed that it's completely homogeneous. However, we liked what you just said, and we use this for rail, because rail, you have big 3-inch aggregate. The voids is around 35%. So I use a much higher frequency in order to get the scattering. So if I can see the scattering, I don't even need to do analysis. Let me show you just one thing here. In railroad, yes, exactly, go here. In railroad, this scattering that I'm seeing, if you have clean ballast, you see it just like this without any analysis. If you get this voids filled with clay, you see it like this. By looking at these two, can you see the difference? Without analysis. So this one here is a complete scattering because the wavelength now, it's closer to the void, so you have internal scattering. But in asphalt concrete, the wave is so big to see this kind of scattering. But I did mention that you lose some power while you are going because of these little scattering, but they are not that much. Yes?
My question is about, can you see cracks and things like that, the quality of it?
No. I think I'll tell you this little story here, if I may. When I was doing my PhD, I read a very nice NCHRP by some people. I don't want to talk more because Joe will know now, but so I read this NCHRP report, and that NCHRP report, it says that you can detect voids underneath concrete. And that's what got me excited about GPR. So what I did, I was at that time at Penn State, and they have a test track, so I went there and made cores, and excuse me, I made voids of, at that time, 1.5 to 2 inches, and some filled one with the water and put this concrete back and so on. And there were 3 GPR at that time, period. And got the 3 GPR, and none of them could detect any of that. And of course, the resolution at that time is not good and so on. Do you know what's the air void underneath concrete? Usually maybe 1/16 of an inch. So it's nothing. So anybody, and there is articles still written, anybody tells you that they can detect that void with GPR is absolutely not true. It just simply cannot. I mean, theoretically, it's impossible. It's not even close. I mean, we did sophisticated signal analysis, but we cannot reach to that level. So cracks, it depends now when you are talking about cracks. If you get the cracks inside that, it's good size and filled with water, you may be able to see something. But if it's a hair crack inside there, even if it's filled with water, you cannot see that because the wavelength is big. So frankly, that's what excited me about studying electromagnetic waves then, because what I read is something I could not even see. And I read a couple of equations, and I said, it's impossible. So the guy is a very good friend of mine who wrote that report, of course, and I reminded him of this. But he's a concrete guy.
Oh, yes, he is.
Yeah, a follow-up to his question.
Yes.
It's from a different field. There are a lot of retaining structures where, water retaining structures where you need to do a lot of analysis, non-destructive analysis, where there are a lot of cracks and all that. So the possibility of water coming out of the retaining structure. So can this, or probably something similar to this, can it be used?
If there is a little crack in the structure that it seeps a little water, I would use myself an impact echo or ultrasonic and so on. That will be a little more effective because it's also localized. It's definitely going to work much better than GPR. Yeah. Now your question. I'm leaving that.
You know me, I'm at that point, I don't ask questions. I think for our associates that are here, the reason this work is so important, and I think Imad made that pretty clear, but pavements are a weird structure, frankly.
Yes.
Very weird stuff. And very often, when folks are trying to understand what's going on a particular highway or runway, you don't really have very good records. You're not terribly sure how thick it is. You're not terribly sure how it was built.
Yep.
If you are, you're lucky.
That's true.
And things go wrong with these things. For example, water. Water
Yeah.
gets in them and it causes, it causes what we call stripping.
Yep.
It's kind of like corrosion of reinforcing steel and concrete.
Right.
In a way.
Yes.
Because it loses all of its strength. And these techniques that we've been working on allow us to see that actually
Yep.
rather clearly.
Right.
And so pavements, a lot of material, probably the most manufactured material of anything made by humans. We probably know the least about it
That's
when we
true.
build it. And again, these are the kinds of techniques that we need to assess it because it's $1 trillion industry.
Right.
In effect.
That's true. And actually, I wanted to add something that GPR got a big hit because when people trying to detect voids underneath concrete, they could not. So they said, we don't want to use this technique. And that put it on the shelf for at least 10, 15 years.
I
And
agree
I
with
think,
you.
I think you can add more than
I
this
would
one,
agree
right?
with you.
Yep.
And they were just wrong about the whole void thing anyways.
Absolutely, because they were wrong. People try it, it doesn't work. Then they will say these things doesn't work.
It just really worked
Yeah.
better.
That's true.
So, Imad,
Yes.
I would like to interrupt you to
Yes.
wrap up, but we do
Absolutely.
have time to use this room until 11 o'clock. So we have a reception to follow.
Yes.
So, I'm not a payment person, but I was
We can
really
make you.
enjoying this presentation. That was a very excellent talk. Thank you very much.
Thank you.
So we have a reception to follow until 11 o'clock. So I know some of you may still have questions. You can stay around, keep talking to Professor Qadi. Thank you, everybody, for coming.
My only other question was,
Thank you.